Okay, so welcome everybody. Let me start off by introducing myself. My name is Randeep. I am the Program Director for the CQF and also the Director of the CQF Institute. So I just wanted to start off by just saying a quick welcome. I certainly recognize some of the faces in the room as people who have part of the CQF, and hopefully many of you online as well. Really pleased to actually introduce Julia Computing. This is our first CQF Institute talk of the year, and it was really nice that we could partner up with Julia Computing and actually provide this event this evening. So just very quickly about the Institute, those of you, many of you will already be members. If you are interested in these kind of talks, then please feel free to join the Institute, cqfinstitute.org. We have a really good set of talks coming up. Now, the next one actually is going to be a really interesting talk. Paul Wilmot is actually just written a new book, and so this will be a first exclusive. It's on the 25th of April. The book's name is called The Money Formula, Dodgy Finance, Pseudoscience, and How Mathematicians Took Over the Market. So if you are interested in hearing Paul, I think he said name a few names, then please, the registration will be open from next week, but you have to be an Institute member. So it is free to join, cqfinstitute.org, so please go along and join. And I think after that we have Bill Zimber coming along in May as well. So there's lots of things happening, and you're all welcome both live and online. So as I say, I just want to do a very quick introduction. Welcome you all along to this evening, and also thank Julia Computing for hopefully what will be a very interesting and very informative set of presentations. I think there's a really good agenda for the rest of the session. So very quickly I'm going to hand over to Viral, who's the CEO of Julia Computing, who's going to say a few words.
Thank you for being here. I'm the CEO of Julia Computing and also one of the co-founders of the Julia language, along with my co-creators, Professor Alan Edelman at MIT, and then Jeff Bezanson and Stefan Karpinski. We have an amazing session planned for the next couple of hours, and I won't get into too much of discussion about that. I think you'll see as the speakers come up. We have a few presentations from Julia Computing about where Julia is today. I'm going to give an introduction. I have my colleague Simon, who's going to talk about a contract definition language that we built in Julia. Then my colleague Avik is going to be speaking about Julia Run to scale Julia programs to large-scale computing platforms. And then we have a talk from Tim Thornham on Julia at Viva. We've got Matt from Bestex talking about MiFID compliance codes in Julia, and we have Gonzalo from Azure, there you are, who's going to talk, or from Microsoft Accelerator, who's going to talk about Julia on Azure. So we're going to keep this tight. We have a lot of material to cover, and hopefully get you all the information in the easiest and simplest forms. I'm just going to speak a little bit about the first few slides. So all of you are familiar with the dynamic languages. I think many of you out here might be Python users. Maybe a quick show of hands. Python? Oh, fewer than I would have thought. MATLAB? There's a few MATLAB users. Any R users in the audience? Okay, slightly different audience. C++? All right. So there's a sprinkling of all kinds of different users out here, and the reason we started Julia was because we wanted a language that was easy to use, that was as easy as any of these languages but as fast as C. So usually it was believed to be a law of nature, right, that you can either have a programming language that is fast or a programming language that is easy, but not both at the same time. And this is where what the takeoff point for Julia was for us when we started working on it. So if you could just start it on the next slide, then it would be easier. All right. I think while we are figuring this out, I can talk about this performance chart right here. So this is a word cloud of various dynamic languages that many of us are used to over the years. But here's a performance chart showing how Julia compares to many of them. And there we go. If you're right on this line here, that means you're as fast as C. If you're above, you're slower than C. And if you're below that line, then you're faster than C. So as you can see on a variety of small micro benchmarks, Julia is as fast as C in most cases, and significantly faster than many of the other dynamic languages that personally I have liked to use before I came up with Julia. I guess the only point I want to make here is that do not believe me when I say this, because everyone sees these charts and they're like, of course this can't be true. How can you be 10,000 times faster than blah, or 100 times faster than blah? So please go ahead and download Julia when you go back and try it out for yourself, and prove to yourself what the benefits can be. Another message that we've often found that resonates and that people have discovered as they've adopted Julia is that if you look at the traditional finance workflow, you have quants or actuaries or specialists who write codes in a more mathematical and dynamic language, and then you have computer scientists or programmers who put those codes into production. With Julia, we think that we found the right blend. We think that programmers as well as the specialists can collaborate on the same platform, speak the same language, and that brings new possibilities to the table, new kinds of programs, new kinds of codes, new levels of efficiency, new levels of performance, leading to innovation that was not possible before. Couple of quick quotes. This is Waters Technology covered an article on Julia. It's a magazine for technology, finance technology, and we also have another quote from Cooper Tires, which is a tire company in Ohio. So Julia is being used widely all over the place. It's not just in finance, although finance is one of the largest adopters of Julia, but Julia is being used by everyone, and I have a couple of interesting slides for you there. It's used around the world. This is a map of GitHub stars. Research is anchored at MIT, but we estimate there to be 250,000 users of Julia worldwide based on our download stats. We do JuliaCon every year. Traditionally, it's been at MIT. And the first JuliaCon only filled up half of those stairs out there, but over the years we've been filling up more of the stairs, and I think by next year we'll also fill up the sides. So that's our goal going forward. It's 250 people attended last year and 50 talks. JuliaCon 2017 is planned for planned at UC Berkeley. We have academic roots, so we are almost always, our conferences are almost always held in academic locations and have a very academic feel to them, even though increasingly you see a number of speakers from the industry submitting talks. We have some amazing talks that have already come in this year, and JuliaCon 2017 is expected to be very special because we plan to announce Julia 1.0 out there. All right. So a number of industries that are using Julia. One of the, finance, of course, I think you've all heard about it, and that's partly what has brought you here, as well as many of the folks online who are listening to us. One of the most amazing use cases has been the New York Fed, which uses Julia for its models of the US economy. The Quant Econ research group led by Professor Tom Sargent has been using Julia for a while and now has conducted workshops and trainings for 7 central banks worldwide that I know of. So, not just the industry, but the regulators are also adopting Julia very quickly. But a completely different application is Julia for collision avoidance that's being used by the Federal Aviation Administration. Folks who are writing the next airborne collision avoidance system are specifying it in Julia, and this is expected to go on every aircraft a couple of years from now as soon as those advisories come out. This has been in development for over 5 years, and it predates even the existence of Julia computing. Just to tell you, and I think this won't be news to any of you, they're still using Julia 0.3, which is one of our oldest releases, because regulatory work is very demanding, and it has to be done with utmost care. So they picked Julia, and they're still gonna ship with that old version. It was one of our best releases ever, so I love Julia 0.3. UC Berkeley, there's a group at UC Berkeley that's using Julia for self-driving cars, and they're actually. Can I switch to a video out here? There's a company called Voxel 8, which is out of Boston and uses Julia for 3D printing and controlling the head of a 3D printer. So The point I wanted to make before I dive into the world of finance is that Julia has a number of use cases. It's used in a number of universities, a number of research projects, a number of industries around the world. So this is a self-parking car video. It's a drift parking video that's been put together by the folks over at UC Berkeley. Is it visible? Maybe if we can, yeah. So this is, this car is actually running Julia on it, right? It's not like remote controlled or anything. This car is looking at the environment around it, is running Jump, which is Julia's optimization software, and figuring out how to sort of drift into that parking spot out there. So with that, we'll switch into some of the use cases and the products that we have that will help you use Julia. Right after this, the next few slides are about the products that we have, and we essentially have 4 products that make it very easy for you to use Julia. Now Julia is open source, and you can just go ahead to julialang.org and download it, and you'll get the Julia compiler and a command line to use it with. There's over 1,000 packages that the community has contributed on Julia, and there's a beautiful IDE that Mike right here has built called Juno. Feel free to bug him about it afterwards. We have a debugger that Julia Computing has put together. We have a bunch of packages that we have put together. It's a distribution that we call Julia Pro, and it's a single-click download, get it installed, get it going. So I'd recommend you to go to the juliacomputing.com website and download it from there. Is that? Yeah, thank you. We have Julia Box, which is largely used by universities. It's Jupyter notebooks running hosted on the cloud, and you'll be seeing many of those demos there. Julia Run is our scaling platform, and we'll have some demos on Julia Run as well as we go along. And then finally, Julia Fin, which is our finance tools to make it very easy to value contracts and price them. So that's a screenshot of Julia Pro. It's integrated well with Excel. So you can just do all your stuff in Excel and see. You can actually work in Julia and Excel at the same time and see sort of results in the spreadsheet update as you go along. That's the screenshot for Julia Box. You'll see more of that as we go along, and you'll see more of Julia Run and Julia Fin as we go along. All right, so several use cases. We have Tim who's going to talk very quickly about the Aviva one, but I'll go through the other ones. Conning is an asset management company based out of Hartford, Connecticut, I think, and they use Julia to replace K for a lot of their insurance economic scenario generators, up to 10 times faster and much nicer code. While performance is why people often come to Julia, it's actually the experience why they stay with it, right? You often come for the performance, but you stay for the experience. That's what we've seen all along. And that's what really brings people, right? It brings new levels of efficiency and ease of use and code structure. We've implemented the Stack industry standard derivatives benchmark. We're as fast as some of the fastest implementations by Intel. Some amazing performance compared to other mathematical optimization software. We have BlackRock using Julia for their time series analytics. The Brazilian Development Bank uses Julia for all their balance sheet risk. This is a report that's produced by Julia running in Docker containers and overnight, and a report that is presented to their board every morning. So the whole thing runs in Julia and Jump, which is a mathematical optimization package. Very quickly on machine learning, we have all the usual machine learning libraries fully available in Julia, as well as many Julia native libraries as well, and they run on all various kinds of hardwares and in the cloud. An example is this lending club data set for financial fraud. So this is a P2P lending data set, and we've been able to put this data together. At the bottom you see what the data looks like in raw form, and then the last 2 rows show you what you need to transform it into in order to do deep learning on it. We've been able to do 2.5 million predictions per second on the CPU in Julia. So that's actually quite impressive, for any level of fraud detection that you may have to do. This is actually much faster than traditional fraud detection engines that run. We have an application in astrophysics that's using 8,000 cores on one of the world's largest supercomputers to build a catalog of the sky. It's a machine learning algorithm presented at NIPS. Not going to go into details right now. Recommendation engines faster than Spark. Deep learning for detecting diabetic retinopathy. This is a medical use case. neural style transfer. This is really cool actually. It can actually learn the style of painting from an artist and paint any picture in the same style. If you'd like your photo painted by Van Gogh, just see us afterwards. Mathematical optimization, I touched upon it a little bit. Julia has some of the best mathematical optimization tools out there today. Actually, I correct myself. It's actually the best mathematical optimization, and it was built by 3 students at Sloan School of Management at MIT, Miles Lubin, Ian Dunning, and Joey Huchette. It's a very sophisticated set of of libraries and Julia packages, which are stacked together beautifully and make it incredibly easy to do any kind of optimization. Jump and Julia are used for all these applications: train scheduling, self-driving cars, electrical vehicle charging, power grid control, plasma physics, fantasy sports. Actually, I think the fantasy sports and the sports betting applications are right here from London. So, if you have a choice of several languages, it is, all things being equal, a mistake to program in anything but the most powerful one. I didn't say this. It's Paul Graham. If you heard of him, co-founder of the Y Combinator and also one of the early Lisp guys. So, with that and no further ado, I'll hand over to Tim who'll talk about how Julia is used at Aviva.
Thank you, Viral. So I'm going to give you a talk about how we've started to use Julia at Aviva. And I'll take you through sort of 3 sections broadly. I'll give you a little bit of background about Aviva, who Aviva is. I guess this is a fairly wide audience, so potentially you may not know about Aviva. And also some of the things, the background to the calculations we're doing around Solvency II and who the team are that I look after, FMS, the Financial Modelling Solutions team. I'll then take you through our initial implementation, some of the thinking that went into it and what we ended up with, and where we're going to be going sort of later this year and beyond. So I hope that's interesting to you. A real life example, I'm not actually going to do a demo or anything like that, but this is a real life example of a Julia implementation that's now in production and being used by a number of our users across the Aviva group. So a bit of background first. Aviva, for those of you in the UK, you'll know who we are. We're a large UK insurance company, I think number 2 after Prudential. And we operate mainly in the UK, about half of our business, but then we're also spread across the rest of the world, in Canada, Europe, many of the markets in Europe, and across in Asia. Over 300 billion assets under management, so a fairly large organisation. And my team has been focused on building out models for Solvency II. So Solvency II, if you're in the banking world, you might have heard of Basel II. Solvency II is sort of the equivalent sort of risk sensitive capital framework in the insurance world, primarily in Europe, although there are look-alike sort of regulations springing up in other parts of the world. It had a huge, very, very long gestation period. It's been talking about it for years and years and years. It's definitely more than 7 years, but we've been actively developing our Solvency II modelling and processes for at least 7 years. And we went live finally last year, at the beginning of last year. And you can either follow a standard approach to your capital models, or you can follow an internal model approach. And to follow an internal model approach, you've got to sort of go through a number of hoops and get it approved as an internal view of your risks. And Aviva went through that process, and we were granted internal model approval in 2015. And because of the long period this was developed, we actually bought our platforms back in 2010, a product called Algorithmics. It was actually part of Fitch, coincidentally, at the time. It later got bought, and this building and this room is part of the Fitch organisation, yeah? Anyway, so you may be aware that you sold Algorithmics back in 2011, I think it was, to IBM. And it's a banking system that's been used for many years. And we licensed it, and a number of other companies licensed it, and it's got a very prodigious user base in the insurance Solvency II world, the big multinationals, and in the UK, Prudential L&G, Allianz, the largest insurance company in the world, AXA, Zurich, Generali, to name a few. So, good pedigree. And of course, you know, we integrated it into our internal model solution. And what I'm showing here is a picture. You're not supposed to read all the details, so don't worry about that. But there's all these flows of data that come through the various businesses and are presented up into this sort of global tool, which is highlighted by this blue box in the middle, where we process that data, simulate different risk scenarios, generate capital outcomes for our balance sheet. That calculation, then we look at the tail and look at the 1 in 200 VAR, and that generates our capital number. And all along we've been pretty much putting algo at the heart of the internal model. And in fact, we created our second, so I started in 2011, a couple of years later we created our second version of it, so second generation, which was much faster than the first one, much more granular. We could run 500,000 scenarios, not 100,000. And it had a front end, a web-based front end. Of course, going back 2010-11, these things were not quite so everyday as they are now. And we actually won the best risk engine in that year. So there we are, up at the awards. So very pleased with what we did with Algo. But I guess we then toiled on for another couple of years. And by 2015, we got a little bit frustrated. So the algo system really wasn't keeping up with where we wanted to go. It was very difficult to change it. We had to go back to the vendor, IBM, make change requests, pay for changes. There'd be a long process of going to Boston, off to Amsterdam and back again, and we'd eventually get what we needed, but it was a long process and quite tortuous. So we started to think of what a better solution would look like, and we'd looked around at proprietary solutions, but still Aviva had quite a lot of peculiarities in its solution, a big organisation with some very specific aspects. So we decided to build our own solution with best-of-breed components. We wanted it to be very fast. We wanted this continuous self-service for the users. We wanted to integrate it with the businesses that were standard formula, so that we could do what's called a partial internal model, and we could report the numbers out into our QRT reporting templates. And we wanted very fast run times, 5 minutes, all in the cloud, instead of on our HP data, on our data center in Newport, Wales. So we had this sort of vision that we could do better, and we sort of knew some of the framework, but we didn't really have a calculation engine. But when we were looking, I sort of keep an eye on these things, and I came across the Julia language, and I thought in my own time I'd just prototype some of the calculations. So we took some of the core calculations, one of the loops that's the most intensive loop in the system, and it's only 200 lines of code, or well, I don't know what it is in Algo because you can't see it, but in 200 lines of Julia, we managed to build that calculation, feed in our group data, and reproduce the algo numbers from year end 14, I guess it would have been at the time. And after a few goes, after a couple of weeks of playing around and understanding how do you benchmark these things, how do you put them in function, you know, making all the basic beginner errors, pushing things to the outer edge of the loop, sorting out integer powers and looping those around so that they sort of inlined and compiled fast. We got the calculation, which would have taken 40 minutes in Algo, to run in 12 seconds on one desktop computer. And at that point, you know, and every week I could see this runtime coming down. I thought, it can't be that fast, it can't be that fast. And eventually I think we got stuck at about 30 seconds. I thought, that's very quick, and suddenly it went down to 12 seconds. And just the syntax is so simple, and in fact the code looked, from when it was running slow to when it was running fast, the code hardly changed, but you just had to learn a few of the basic things not to do. And as long as you didn't do those, it ran super quick, and the code didn't need any special clever sort of syntax. So I loved the elegance of the code, the simplicity that Viral was talking about, and this fantastic speed. So from my perspective, the actuaries, the quants in my team, this should be a language that they should love, and it's giving us that speed that we couldn't get out of a proprietary solution. So of course that was just the start. We then needed to show that we could do the whole calculation, and this is a sort of a map of some of our calculations from left to right here. So some of the inputs, simulating risk distributions, generating a loss distribution on our balance sheet over 100,000, 500,000 scenarios, the assets, the liabilities, different parts of the business adding up through the group reinsurance vehicle. We aggregate that up, we rank it, we look at it by risk, we look at it at total capital level, we allocate down to risks, and we produce a number of different outputs for the different businesses at the group level, different percentiles. So there's quite a bit of functionality that over a period we'd built. So we needed to build this into IM3. Luckily I had someone in my team who's much better at coding than me. In fact, a couple of guys in the team who then took this on. And the guy eventually built most of it, Hugo, I'll give him a name check, Hugo Tam, did an absolutely fantastic job. And probably in about 3 weeks, maybe 4 weeks, he'd got broadly the whole calculation working. Now, it wasn't the full-end final version with all the different outputs and all the different inputs with flexibility, but broadly it could do the calculation end-to-end and reproduce year-end 14 numbers. And you can see some of the remarkable runtimes that we got from the system. And this was not after months of tuning, this was first time through. So instead of algo taking 2 hours 30, if I take a sort of a slice through these different steps, we could get it running in about 2 minutes. And this was on one desktop computer instead of algo, which was running 500 computers on a remote data center. Now, it wasn't using all of those at one go, but it was using a chunk of them. So at any one time, you might be using something like 30 very high-spec computers instead of one desktop. So sometimes I talk about one of the core bits of the calculation is 30 times faster on 30 times more compute. So I basically round that up as 30 times 30 is 1,000 times faster, sort of core for core, if you like. So you might hear that. I think it's somewhere on the Julia website. That's where that number comes from. So very easy to pick up. Very easy to regenerate, numbers that we had an Excel spreadsheet, so we knew the calculations that could, and we needed to turn that into a working Julia bit of code. So were there any problems? Well, probably 3 challenges along the way that nearly tripped us up. Well, didn't really. We knew we could solve them. It just took us a bit more time. The first was we sample a lot of distributions. I'll just take you back there to the previous slide. That risk factor scenarios bit, the bit that takes 1 hour and 30 on algo. There are 1 or 2, if you're sampling a log normal or t-distribute, they're very quick. There are simple ways of getting a particular percentile from a CDF. But there are 1 or 2 tricky distributions, and we have one in our data set, hyperbolic distribution, that we use many times. It's well known for it's a sort of fat-tailed distribution that you can apply skews to and things like that. It's commonly used, I think, for equity fat tails of rare events. And anyway, that's one of the data points that we've got. And sampling that is a very complex calculation. There aren't any closed form solutions. You've got to do it by numerical integration. And if you try putting that into R, it takes forever. There are some tricks to speed it up. What we eventually did was we just went through one very, very fine-grained pass. The PDFs were pretty quick. We went through the whole thing, adding it up so that obviously if you add up a PDF, it should add up to a CDF to be 1. And we could get that, and we could check that the error was small enough, and if the error was big in any particular step, you could just halve the gap and smooth that out. And as you go through that, adding it up, you know where you are in your cumulative distribution, just to output every 10,000th quantile. So it's a single pass through your distribution, output all your quantiles, and then you can interpolate those. It's a very fast way of generating a lot of points on a very complex PDF. So that's how we solved that one. And actually, we could, because we knew it was the right answer, because it added up to 1, we could check it against R, and we found actually some bugs in the core R distribution for, for hyperbolic. The next one was the nearest correlation matrix problem. So we have correlations between our different risk drivers. When we set those up, there's a process where each business sets them up and then we fill in the gaps, and it's a big correlation matrix, 200 by 200. You can't possibly set every single point and make it Cholesky decomposable for a a correlation matrix requirement to generate correlated normal 0 ones, which is our basic requirement. So we need to create an equivalent correlation matrix to something as near as possible. So there's quite a lot of academic literature around this. We had in algo something called the Rebennato-Jackal method from 1999. So we had a look at it. We found a better method, the Higgum-APM method, with a bit of a speed up on it. We implemented that, and we've got a much better technique than we had previously in algo. So again, that's a great one. At some point, these should be put into some standard package, these techniques. I know distributions package, whatever it is doesn't have the hyperbolic, so you should put it in. But it is quite a tricky one to get to run at speed. Right, there you go, Simon. It's used more widely than in Aviva, I believe. And nearest correlation, you can go to the NAG library, MATLAB, they've all got these sort of NCM type algorithms, so it's again something you might want to look at. Reproducibility, one that's still tripping us up, just came up the other day, that we've got different instances. We have desktop where we do development, we've got cloud, small servers, large servers, and we really want, with the same random seeds, we should get the same numbers, and we do occasionally at the very, very extremes of our calculations do get very minor issues, and unfortunately, because of the way that the random normal ones are created, any tiny error, and these are out of the 10th, 12th significant figure, they can ripple through and change the order of the simulations, which will create a small simulation error. So we are still seeing one or two of those, so we've got to nail those. But those are some of the things that we found quite tricky. But I think you'd find, I'm sure in any application you'd find some things tricky if you're trying to reproduce a proprietary system. So that was our project. We went live, this is how we're tracking. So this is an example of month by month. We have some various service targets. Our users we check that we're meeting our service targets. So how available has the system been? That's obviously a factor of how robust some of the framework around Julia is. It's not just Julia, so we've got a fairly big framework around it. We're on Amazon Cloud, so it depends on that as well. And occasionally there are little glitches, servers go down. We have a run performance target for the business units for group. So we want to complete in about 20 minutes. That's our target for business units, and we easily beat that. We've got green all the way through. Our group runs 45 minutes is our target. So these are longer than the benchmarks I showed you a minute ago. Benchmark of about 2 minutes was a business unit, and we broadly keep to that. That was in the early version. Now we've built it out, and we're running a lot more reports, 500,000, not 100,000. So the runtime sort of go up fairly linearly with those sorts of factors. So we're running at more like this sort of 20 and 45 minutes is top end of where we want to be. We want to be within that target. And you can see the group runs, had a few problems with the group run, so we put a few more big servers in, and that speeded that up. So there's less queuing. As more requests came in, occasionally they'd queue, and that was the reason, rather than slow run times. And we want to reduce the number of failures, so that's about trapping inconsistent user inputs, that sort of thing. So those are some of the benchmarks. So we really treat it as a true production system. It's live 24/7, any day of the week the users can use it in all those different businesses around the world. There's an example or an indication of the number of runs going through a month. It's not a huge number. I mean, 1,400 there's our record in January. I guess it depends what you think a large number of runs is. People don't really do these for fun. It's part of their job. They have to produce numbers. I guess if they were playing around, they might do more runs, but they have other things to do in their day. This is sort of proper production work. So they'll do base runs, they'll do sensitivities, they'll do roll forwards each month, and then there's quarterly processes, plan processes, and this spike is at year end. So year end is a big process for us. And you can see a breakdown there of some of the businesses, and see the big purple bar there, that's the UK Life business, which is our largest business. Okay, so that's a bit about how it's running in production. Lots of users all around the world running it. Where do we go next? Well, we've built our first application. Finn, who's in the audience actually, there you go, put his hand up. He's helping us to rewrite the credit risk system, which coincidentally is also another algo system. It could have been another system. We're actually looking at a third system as well, which isn't algo. So we intend to transfer that. We're very pleased with Julia, and there's no reason why we can't repeat the same trick. We're pretty confident we can reproduce the calculations in Excel. If I can do that, then I can definitely put it in Julia. So there's no reason why we can't do it. What we'd like to do, and I'm interested to know a bit more about Julia Run in a few minutes, we're actually looking to put it on Spark and distribute through Spark as a sort of a cluster management capability, probably because we may use other solutions. We might write some C code, and we might sort of mix and match a bit. So this gives us a bit of flexibility, although at the moment our main use cases are Julia. And Avic and others, Simon here, we're hoping, Avic's definitely helping us with the Julia binding for Spark, and Simon, I'm hoping, can come on board and help us sort of with some advice about how best to build in this sort of distributed Spark world. So this is going to be a heavier use case, I guess, that we've got to get into production. Meanwhile, we want to look at optimizing the IM3 solution, the first one that we were talking about. So that's where we've been, that's where we're going. We're now, I've got a couple of people in the team who are very skilled in Julia. We're now branching that out and building more skills in the team. So that's our story so far. More to come, I guess.
Yeah, thank you. So my background, I've been working for Julia Computing now for a year and a half. Previously to that, I've been working with Julia generally since about 2012. So pre-version 0.1, so quite a long time actually. And it's one of those things where I I came from sort of using MATLAB, and simply because I was very unsatisfied and wanted something a bit faster and easy to use, and then sort of stayed contributing to Julia and working with Julia more generally because of the power and flexibility that it gives you to do things, and sort of the expressibility you can do to express ideas that really are very difficult or complicated to do in other languages. And so this has led to this package, Militus, which is part of our Julia Fin package, which is now available. And I'll try to give you a flavor of what makes it powerful, how it can sort of work well beyond what is possible in other languages, I guess. So Militus is a Julia package which provides two things. Firstly, it's a contract definition and specification language. And on top of that, it's also a library that sort of will then automatically adapt and value those contracts under different assumptions. And what makes it sort of work under the hood is that it's based on leverages many of Julia's very powerful features. In particular, extensively uses this sort of generic programming and multiple dispatch, if you're familiar with those. It really pushes to limits Julia's just-in-time compiler, and we really make use of things like features that Julia has such as fast user-defined types, which are not really possible in other languages. And we also use a few of these third-party packages that have developed around the language, in particular one neat one called automatic differentiation, which I'll sort of get to near the end. So a contract specification language, the idea is based around this, well actually it was inspired by this paper by Simon Pitton-Jones and Jane Makiba, where they sort of developed sort of a computer program. I think they wrote it in Haskell, which reasons you might sort of come to appreciate soon. But it turns out that Julia is actually a much better language to do this in, just simply for performance reasons, and that so they developed it as a sort of nice, idealized language, how you can express things. And I think we've taken it and then showed how you can actually, not only is it nice and idealized, it actually works really well in practice. There's no sacrifice to performance for using this thing. So the idea is that the contract language is built around this sort of very like core primitive contracts, which you then build up and compose. So the simplest one is this receive contract or amount contract also, which you receive. So the simplest possible contract is you receive something. So the contract is I receive 100 units. There's also then the opposite side of that contract, which is you give so I can pay 100 units, which is essentially constructed of a nested contract, so a give contract, which says I'm going to take the opposite side of the containing contract, and then within that I'm giving away this receive contract. So it's sort of this we can a very simple idea of how you can construct the opposite these contracts from sort of these small units. So there's two primitives here: the give and then the amount contract. And on top of that, one of the things we've built around to it is this idea of units, particularly currency units. And so we can Julia uses implicit multiplication. So if you stick a number outside of a variable, it multiplies them together. So this is 100 times USD, which happens to print nicely when you use units because it's just 100 USD. So pay 100 US dollars. So rather than just dealing in abstract units, we can actually stick units out to the side of these things, which can be quite useful. So we have this contract called single stock. So this just represents sort of an unknown stock price, or I might rename it. Probably get renamed at some point, but it's going to be it's sort of an unknown which we wish to build on in future. And so then we can buy that. So we can have a simple contract where we buy it. So for example, we purchase the stock for 100 US dollars. So to purchase a contract, you have to both receive the stock, and then you also have to give the amount. So it's sort of this composed from this. So both is like both sides. Both contract contains two nested contracts, and then we do that. So that's a contract to purchase something. And then from that, we can construct something like a zero coupon bond. So a zero coupon bond is just a similar thing. You can receive something at some point in the future. So a zero coupon bond is made up of a when primitive. So when primitive means that I don't get it now, I get it when some future condition is true. And so in this case, when the observed date is 25th of December 2017, I will receive 100 US dollars. So that's a very simple way to express a zero coupon bond. And you can think of other things like how I construct, a general bond is I just compose multiple boths together to get this boths over zero coupon bonds. Another interesting one is an either contract. So this is sort of the fundamental idea of options. So in either contract, you either get something or you get one contract or you get the other contract. So both contract, you get both of the containing contracts, and either you get one or the other. So there's sort of a zero is a null contract, so you get nothing, or a single stock. So in this contract, you get either a single stock or nothing. And so here's sort of a canonical way to express a European call option. So at some point in future, so the when, it's a when contract, so when the date is equal to December 25th, 2017, we can either receive nothing, i.e. the zero contract, or we can purchase a stock for an amount, 100 US dollars. So that's simply a way of expressing the future intentions. And similarly, an American put contract is rather that we replace the when with this anytime. So a when contract can only be executed when the condition is true, and anytime can be executed anytime while the condition is true. So in this case, we can execute the anytime contract anytime before the date anytime the date observation is before December 25th, 2012. So that's the only difference between those two. Okay, so that's all neat. We've got a way to express these sort of nice contracts in very simple elements. But what does that get us? So a contract is sort of one part. So typically, the standard approach is you want to value a contract. And so a contract itself only captures certain aspects. In particular, only captures these sort of objective ideas. So the things like strike price, maturity, maturity date, etc. They're sort of the objective things that are fixed. They're not changing. The other part that we need is sort of capture the sort of varying or the sort of the subjective part. So these can be things like current price, or the interest rate, discount rate, dividend rate, and of course things like implied volatility in the case of option pricing. So there's no such thing as an implied volatility. So the subjective thing that is that we impute. Okay, and so this is a quant finance thing, so we're required to contractually obliged to have a geometric Brownian motion. So the workhorse model of quant finance is this, this standard it's a Brownian motion. Well, Brownian motion with an exponential in there, if you want to think of it, how I think of it. And so this is the fairly simple model. So this says essentially this stock is going to follow this geometric Brownian motion model, starting at today, where its current price is $100 US. We have a few other things in there. So there's 3 extra parameters. So the first one is the yield rate, so the risk-free rate. The second one is the carry rate. So think of this as your continuously compounded dividend, or if it's negative, it's cost of carry if you're dealing in commodities. And of course, sigma is our volatility. So these can be all. There's a few more things under the hood, so you can express these things, use different sort of forms of discount rates as well, and make these more flexible. Okay, so we can use the value function as a thing now that ties all this together. So basically, a value function takes 2 arguments, the first argument being the model, and the second argument being the contract. So value, so you're saying, you're valuing a contract under the assumptions of that model. Okay, so the simplest contract is we receive the single stock, and since the current price is $100 US, then the value of that contract is $100 US. More interesting, so say we have a contract which will let us purchase the single stock for $80 US. Now, so obviously risk-free, arbitrage, etc. The value of that is then, the value of the contract is then $20 because we could purchase it for $80 and then sell it for $100. So yeah, the implied value there. Okay, and then something more general. Here's sort of here we've got a when at, we can buy a single, so it's a buy single stock at some, but only at some future date. So this is now a future forward contract. So at December 25th, 2017, we can buy this contract for $80. And so the value of this is, is that value at that point in time discounted back. So it automatically infers all those values of those contracts. And what's actually kind of remarkable is there's no code that's special cases these. These are all determined automatically by certain properties of the underlying, certain properties. So the value of a give contract, for example, is simply the negation of the value, negation of the underlying contract. The value of both is essentially the value of both contract is the value of the 2 containing contracts. And the value of an either contract is the maximum of the 2. So these can all be handled by sort of the Julia's multiple dispatch, which is one of these really neat features. On top of that, okay, one thing, and then of course then we can special case, we can also recognize when there's sort of special cases that we know have closed form solutions. So the canonical one being, of course, the Black-Scholes model. So if we're valuing a European call option, then we know under the geometric Brownian motion it has a very specific, you just plug it into the formula and pull that out. So I talked about the units earlier. So one advantage is that these can be used quite easily to catch errors. So if I instead try to price, so this model was specified in terms of US dollars. If I try to feed in a contract with pounds, it'll throw some sort of error. So it won't let me, the units can catch these sort of unit errors, which is sort of the purpose. And because of sort of how Julia works internally, these types are essentially, there's no overhead to using these types because they're sort of all, it's just a simple, the units is just a simple wrapper around a sort of standard floating point type. The compiler realizes that and just elides it all once it can figure out that it's actually not, the units don't matter. So all these errors sort of pop up at compile time in that sense. And of course, not all contracts can be valued under each model. And so, for example, if we have the American put option I defined earlier, there's no sort of closed form solution to value an American put under a geometric Brownian motion. So that leads us to other types of models. So binomial lattice models. So these are essentially a discretization of that geometric Brownian motion. So the canonical one being the Cox-Ross-Rubinstein model. Of course, there's others, but they're all very similar variants. So there's a few extra parameters. We give a start date and an end date, and then there's a number of nodes essentially here. The 1,000 here is the number of steps in our tree. So the number of the width at the end of the lattice. And so we can value the European call option we valued earlier, and we get a very similar number. So what do we get? Previously we had a 7. It's correct to at least 3 decimal places. But we can also value the American put. And what's particularly neat is that, again, that American put, I didn't actually code an American put option manually. That was all determined by those sort of very primitive options with a few extra to deal with these, the whens and the eithers and the anytimes. And okay, this is simulation. So that was, to value that American put option was 3 lines of code. That was defining the model, the CRRM, define the American put option, and then calling value. Here's sort of the equivalent to do that in QuantLib. So this is C++ code. So you can see sort of, doesn't show up that well, but you can see get the idea. You have to define, so this is QuantLib is a very large C++ library, which is, has similar ideas that, expresses all sorts of engines for valuing different types of contracts. And it requires huge amounts of boilerplate simply to get to this same point. There's basically, you have to define calendars, you have to pull out things like yield rates, you have to define all sorts of separate objects for for each different component. We can do that in Julia as well if you want to use special components, but by default it will just stick in, it automatically will define the obvious one, the canonical one if you're not doing that. And then you just define the process, and then define the option itself, and then finally eventually get to the end and you have to call this method. So that was a huge amount of boilerplate code just to do what is essentially 3 lines in Julia. And on top of that, Julia is itself actually faster. So in Julia that took 9 milliseconds. The equivalent one in QuantLib, so I've just wrapped that, calling that QuantLib code, compile that code. So this doesn't include the compilation overhead in either case. Takes about 3 times as long to get the same answer. They're also off by something different about the 5th decimal place there. So I'm not sure what the reason is. So basically, I guess my point is that Julia doesn't, despite all this nice all these contract, despite this nice structure that we build, it doesn't actually cost us anything in terms of performance. That we can, all this performance, the compiler is able to basically realize that all this is essentially niceties for the user and gets rid of it and just compiles down to what is the obvious, loops, etc., arrays, data structures. Also support things like Monte Carlo. So Monte Carlo model. So we feed in so to construct a Monte Carlo model, we feed in our geometric Brownian motion. It takes Monte Carlo samples of it. We can get some, of course, you're doing Monte Carlo models, you need nice plots. So here's canonical nice plot to of some Monte Carlo paths. Sorry? Is it utilized and called the course? In this? No, well, this was just done single threaded, but it can. There's no reason. Yeah. I mean, this is only 10,000. So this is literally, this is probably this is about half a second. And so then, of course, from then on, we can value, the same European call option. There's some it's only 10,000 paths, so there's a little bit of Monte Carlo error. So that's we're off by about in the 1st decimal place. But you can also do things like Asian options, which aren't really possible to do in don't have a nice closed form solution. Well, so a linear Asian option here, so it's a floating fixed strike price. So we receive the average of the price over the last month, and so again, we don't actually specialize write code for each individual option. It just knows that when it gets to this component, it knows that it has to average over the previous month of price. For the moving average means it has to average over the price rather than take the slight single price, and then it aggregates all that and gives us the correct answer. So we're getting to the end. I'll just give a sort of wrap up. So it has sort of the other sort of standard features you'd expect from a thing. So this sort of library, so volatility curve fitting. So we can fit. So here's fit some. So we've got some strike prices and some prices and some the option prices, and want to fit implied volatilities. So there's an implied IVOL. So we define a core model, which is essentially the geometric Brownian motion, sort of the core components that go into a Brownian motion, but without knowing the volatility. And then you fit the implied volatility. The implied IVOL function fits the implied volatility. This dot is essentially a new Julia feature, which says it's sort of an automatic vectorization thing in Julia. So IVOL usually takes one argument. If we stick a dot at the end, it then automatically vectorizes it over and gives us an array of results. And of course, we can then use those to fit more complex models. So here we can fit those prices to the Sabre model, which is it's a 4-component what do you call it, diffusion stochastic volatility model. So we fit the saver model, and then we can then plot the resulting implied volatility curve. So this is the implied volatility curve from that saver. So they're the implied volatilities of the data, of the observed data points, and this is the fitted saver model. So then we can use that then to extrapolate outside the original observations. And finally, I'll mention this. So also supports computation of Greeks, but we do this in a quite special way. So we use a technique called automatic differentiation, which means basically it saved me a lot of work. So I didn't have to go through and write all the derivatives down by hand. Julia has quite powerful features. So automatic differentiation. Who's heard of automatic differentiation before? Okay. So two things to know about thing to know about it is what it isn't. So it isn't finite differencing, it isn't numerical differentiation, and it isn't symbolic differentiation. So it isn't pulling out your piece of paper or plugging it into Mathematica and trying to figure out what the actual derivatives are. Basically, you think of it as just propagating the chain rule, but applying that automatically. So rather than when you feed into a function, you don't feed a value in, you feed a value and its derivative, and that derivative then gets propagated through the function calls. And because of Julia's generic programming, it makes it very easy. And in fact, next month we have an article in Wilmot magazine sort of explaining how this sort of works under the hood. So I won't ruin that for you, but it will be in Wilmot magazine, and probably we'll have some blurb on our website about it as well. So follow up there. But we use this in Militus to compute all those Greeks. So for example, we compute deltas and vegas. And notice we're computing also Greeks for Monte Carlo models here as well. They sort of automatically follow through and compute out the, we can compute the vega of an Asian model quite easily without the Asian option, without any trouble. Yeah, didn't require any effort on my part, actually. Okay, I think I'll leave it there for the time being, unless there's any questions. But now available now to try out. So Julia Computing, you can find the Julia Computing website or at that link there. And I guess I'll throw it to questions. We've got 1 minute or two before Avik takes up.
Thanks, Simon. Right, so I have a quick set of demos about Julia Run, which is our product to scale Julia. As Viral said, Julia Pro is our product for the desktop, for you to develop your algorithms in Julia on your local desktop. Julia Run is our product to actually take that code and run it at scale, either on the cloud or within your own internal clusters. And so Julia Run leverages Julia's parallel programming primitives, but makes it easier to run them, to manage the cluster, to to present your code into the cluster. So I'll just not talk too much about it. I'll be around if you want to know more. I will quickly run through an example of what you can do with Julia Run. And this is only one of the things you can do, but that will hopefully give you a flavor of what capabilities there are and how easy this is. So Julia Run itself is primarily built upon Docker and Kubernetes. So we create a cluster of Docker containers which are all running a single Julia process, and then we orchestrate that cluster using Kubernetes. And this whole thing is controlled from within Julia. So you don't have to leave Julia to do your operations or your deployment. You can do everything from within your Julia prompt or your Julia code. Right? And the demo that I'll show you leverages the Azure Container Cloud. It is running on Azure, and it leverages Azure's Kubernetes cluster management facilities, which is, as I said, called Azure Container Cloud. And Gonzalo, who is from Microsoft, will follow me and give you a little more detail about what Azure can do with Julia. Right, so just to load up my code, I am running this within a Jupyter Notebook, which is an interface into Julia. It's a web-based interface where you can run Julia on the server and sort of connect to it from a web browser, and that's that's probably the easiest way of getting started with Julia. So that's what I'll use. So I have Julia running on an Azure server, and on that server I'm running this code that you see. So I just have a file called portfolio.csv, and the file looks like this. It's got 3 columns. start price, strike price, and a strike date. You see, I have a Unix command head that I'm running. Julia has this facility where you give a semicolon and run any shell command. It'll then run that in the shell. So that again is, makes it easy for you to sort of play around with data while you're developing. Right. So this is what the file looks like. I load the file using Julia's read CSV function, and I say that the file has a header, and I just read it into a variable called p. And then I convert the last column from strings to dates, because they are actually dates and I want them to be Julia date types. So again, this is just calls the date function that parses a date and gives me a date object, right? So this is just some preliminaries to get your data into a form that that is amenable to data science, really. So I see the size of the data. This has about a little over 200,000 securities, as I said, with a start price, a strike price, and a date. And let's consider that these are all American options that I want to value, right? So I have about a 217,000 American options that I want to value using a lattice method that Simon just showed you. So let me do it for 1,000 securities first, because I'm on my desktop. I don't want to run the whole thing I don't want to run the whole thing in one go. So I just run 1,000 of that set of 217,000. The code here is exactly what Simon showed you before. We create a CRR model, and then we create an American put, which defines a contract, and then we call the value method, right? So 1,000 securities, valuing them takes about 2.5 seconds, which is pretty good. It's nothing to sneeze at. But if you think that 1,000 securities take 2.5 seconds, 217 will take a little over 10 minutes. And that is certainly something that you don't want to wait around while it's happening. So it's like it's more than getting a coffee time, right? So we don't want to run it on this machine. So what we do is we leverage the Julia Run cluster. I have a cluster running. I have a Kubernetes cluster that I have started on Azure that is running. Let me just see if I can show you the cluster itself. Yep. Okay. This is the cluster running. Yeah. So this is if you've seen Kubernetes, this is a Kubernetes dashboard that shows you the cluster running, and it has a set of workers, and I'm just gonna run my code on that cluster. So this cluster has been started from Julia. And while I'm showing you the cluster manager, you don't need to worry about it as a Julia programmer or as a data scientist. And that's part of what I want to show you, right? So what you do is from your code, you say initialize. There's a function called init parallel, which is a Julia run function, which basically connects you to that cluster, connects your node to the workers that are running on the on the cloud, right? And when I start, I have only one worker. That's because I haven't sort of scaled my jobs. There's a scale function that Julia Run provides you. This is really the only thing that you need to know about Julia Run, right? There's the scale function that you call that gives you as many processes that you want. So I say I scale it to 20, and I check how many workers do I have. I get 20 after a few seconds. And so let me run my process on these 20 workers, right? So I load my code on all these workers, and this is just a little bit of housekeeping that you need to do. In production, you can get rid of the housekeeping, but if you're doing interactively, you need to load your code on all the machines. Okay, someone's sending me email, sorry. Right. So then comes the most interesting bit, which is running the code on these parallel machines that I just created. So I have 20 processes in my cluster. All that I do is I put this @parallel invocation outside my loop. This loop you see was the same loop that I showed you before when I was running it on one machine. I put at parallel in front of it, and instead of saying for I is 1 to 1000, I say I is 1 to n, where n is 217,000, and this runs the entire data set across these 20 machines that I have given. And you see, instead of 10 minutes, this takes about 70 seconds. So, less than coffee time. So that's progress, and that's useful. And so, you can see how easily you can just spin up a cluster and run this code and get your times down to something that is usable for interactive development. So that's useful, hopefully. But now I want to run this loop or run these valuation across different scenarios. So let's say I want to run each instrument across 10 different scenarios of interest rates, right? So I increase the amount of work that I do 10 times. And again,
can you speak a little bit about what the VCAT is for?
Yeah, sorry, yes, of course. So what this at parallel does is it does MapReduce, right? Most of you have heard of MapReduce thanks to Hadoop's PR. MapReduce is basically you take a function, you map that function across different processes, different machines, and then you reduce the results. So you take the results back and you operate on the results. So what we are doing here is that we are running the valuation, the value method on 20 machines for 200,000 securities, and then we are VCATing or vertical cat, which is a Julia function that basically takes all the results and puts it back into one array, right? So this takes all the 200,017 individual values and concatenates that, or vertically concatenates that into a single array. So this is how you do MapReduce in Julia. It's the at parallel method, which takes your function, runs it on as many processes as you have, and then concatenates or reduces the result back to what you want. So you could, for example, do distributed sums where you do some operation across 100 machines and then sum the results, and that would be sum would be your reduction, right?
If you want kind of very heavy manipulating some data which
Yeah.
you store somewhere else.
Yeah.
So all of these machines, how do they have access to this?
So this is a simple case where we have loaded the data on. We have loaded the source data on all the nodes or all the processes directly, and that's the simple case, and that's the case where your input data is small. If your input data is large, there are various other higher level facilities in Julia. So for example, there's the concept of a distributed array, which is an array that is stored across multiple processes. You can then send your job to the local process which contains that data. So you can do all that collocation, data collocation. You can do complicated scheduling algorithms, and all of that is built in. But that will take me 2 hours to demo, and so this is a simple demo that hopefully gives you a flavor of how easy it is. But there are certainly more complex operations that you can do.
From a network source, right?
Yeah.
Or a database.
Yeah. Yeah. So we will be around again to talk in more detail about this or anything else, right? Right. So this is running through my 200,000 securities. But as I said, what you want to do usually is more than once per security. You want to run it through multiple scenarios. So if you want to run this, for example, as I said, with 10 interest rate values for each security, I increase my computation 10 times. So instead of again a minute and a bit, it'll go back to 14 minutes is what I'm looking at, which again sounds a bit too much. I don't want to wait for that. So what I do, I call scale again. Instead of scaling to 20, I sort of double it and more. I say, give me 44 machines now. And then I wait for a few seconds, and I say n workers, and it's giving me 44 processes, right? And then I sort of do exactly the same. Again, this is boring, right? You take the same code, flip a loop on top of it, put at parallel in front, and it'll run it through all these machines. So again, instead of I've doubled the number of machines, and instead of sort of 12 minutes or 14 minutes that I was expecting, now I'm down to about 3.5 minutes for that. So as your workload increases, you increase the number of processes that you have available, and Julia Run will take care of scheduling them, creating those clusters, connecting those workers to the master process, and distributing the job to that. And that's really the key benefit of Julia Run. So this is again, just a screenshot of the Docker dashboard, and you see that as when I submitted this job, the total number of CPUs across the cluster increased, then it fell back down. So you can track all of that. There's logging, all the goodness that Kubernetes gives you is all available within here. Right? So that was a very quick introduction to Julia Run. As I said, we will be around, and you have our emails. Get in touch if you are interested. But for now, I will hand over to Gonzalo from Microsoft, who will tell us a little more about how Azure helps and how Julia is fundamentally supported on Azure. Gonzalo, please.
So yeah, thank you very much, Julia Computing, for hosting us. It's great to see Julia running at scale on Azure. With this short session, what we wanted to do is talk about the key benefits that you might get if you run Julia on Azure, and the same benefits Julia Computing gets when they run Julia Run on Azure. So this conversation started around 2 weeks ago with Viral. We started talking about why should I use Azure, right? What are the key benefits that I will get if I move Julia Run onto Azure, right? So we'll cover those 3 advantages that we discussed. Before we do that, let me talk a little bit about my team and what we do. I work in a small team in Microsoft called Microsoft Accelerators. In essence, we work with emerging companies that we think that have great potential. It's a global network. I lead the technical program in London. And there are also accelerators in the most well-known entrepreneurs locations, like Seattle, like Tel Aviv, Beijing, Shanghai, and Bangalore, right? In our team, we don't have any specific industry alignment, so we welcome any kind of company. But as you can imagine, in London, we see great momentum with companies around fintech. In Tel Aviv, there is great momentum around security. Seattle, we have loads of emerging companies working around AI in general. So it really depends on the ecosystem. In essence, all we do is onboarding these great companies into the Microsoft toolset and helping them to grow from a business point of view as well. But the purpose of this presentation was specifically to talk about the benefits that Julia will get by running on Azure. Quick question for you. How many of you have used public cloud technologies, whether it's Azure, AWS, or Google? Good. So that's many of you. So I guess that for those who don't know Microsoft Azure is Microsoft public cloud platform, right? So it does very different things, but the idea is that we host large number of services in our global network of data centers. You can use those services and pay as you use those services, right? The key 4 pillars that we focus our strategy on include trust, and we'll talk about what this means, global reach, openness and flexibility, and a comprehensive offering. With trust, you all know work in fintech, right? If you've used public cloud technologies, you probably have bumped into some challenges around pushing for cloud technologies in your organization. And we have learned that this is actually a very important point. Technology is important, but building the trust that your organizations look for is actually one of the key priorities. And we take a 3 pillars approach to build that trust. We'll talk about how we manage security at our global footprint. We'll talk about our global scale and how you can actually collocate data in your markets, how you can reduce latency, right? And how we manage compliance. I've seen that a lot of companies I've worked with sometimes kind of mix security and compliance. For us in security, Microsoft invests in the range of multi-billions a year just in making sure that our infrastructure is secure. And we take a very interesting approach, which we call the red and blue team, right? So we have two teams that are actually fighting against each other. The blue team has to protect the services, and the red team has to kind of detect weaknesses in the services, right? Our approach is always based on no matter how many money we invest in our infrastructure, sooner or later someone might find a weakness, right? So it's not only about protecting it, it's more around how we can, as quickly as possible, identify those possible breaches and also react and stop whatever risk, right? Every Azure service that we offer in our public cloud platform follows these principles, right? The other important point is around compliance. Don't know how much you know about this, but at the moment, Microsoft Azure offers the most comprehensive set of compliance and regulations that we have achieved, right? And we approach this from 4 different points of view. We typically identify global compliance programs that are applicable across industries. They are primarily technology-oriented. Those are the ones that we see at the top, ISOs, SOX, you name them. We also put a lot of energy specifically in the US to work with public governments and the regulations that are specific to public governments, but also in achieving specific regulations that are specific to industries, whether they are payments, whether they are healthcare, whether they are media and entertainment, you name them. And last but not least, also putting a lot of energy in achieving local regulations in local markets, even if those local markets are, technically speaking, smaller, right? So all this information is publicly available. Every time we achieve a certification, we publish this information. Available in the Azure Trust Center. If there is any specific regulation you are interested in, you can go there, check the security controls that we've achieved, and actually get the audit reports as well. The other very important point when it comes to trust, it's not only trust, it's also performance and latency, is global footprint. You may or may not know this, but actually, if you think about the 3 hyperscale cloud providers, Azure is by far the largest in terms of number of locations. So at the moment, we have 34 data centers available online that you can use, right? We are talking about 2 in Germany, 2 in the UK, North Europe and West Europe, multiple in the US, China, we have 2 in China, Australia, 3 in India, Japan, Singapore, and Hong Kong. All these data centers are available to you. So when it comes to host services, you could pick and choose. You could use one, you could use multiple, right? And in addition to that, we've also announced that quite soon we will open 4 more data centers available online. And we take a pretty unique approach in here because not only we offer this large network of data centers, in some specific markets that we've identified that have more stringent regulations, we actually work with local entities and we work collectively with companies based in those countries to provide a different management experience. That means, for instance, in China, despite the fact that it's our technology, those data centers are managed by a Chinese company. The same holds true for Germany, right? So another very important point. In terms of networking, for instance, we are by far one of the largest network cable operators at the moment. So we have communicated all of our data centers with dark fiber. I don't know whether you heard the news or not, but that was in the media around 2 months ago. We recently deployed one of the largest dark fiber undersea water cables in conjunction with Facebook that goes from the US to Spain, so massive investment as well. The other very important point is around openness and flexibility. Microsoft Azure is Microsoft platform, but we welcome actually any technology, any operating system. We've seen Julia run hosted on Kubernetes, which, as you know, is a Google framework. We've seen Julia Run hosted on Docker containers, and we welcome all of these technologies, right? Not only we welcome open source technologies, but actually we are the only hyperscale cloud provider that is also working on a packaged version of our public cloud platform called Azure Stack. This will be an integrated appliance, hardware and software, that will offer the foundational Azure services and that organizations will be able to deploy on-premise, right, with kind of the same API, the same management experience. So big investment for us in terms of hybrid cloud technologies. And again, when it comes to open source technologies, we welcome anything from infrastructure, operating systems, from database, from application frameworks. For sure, you can use C#. We love Julia, Node, Python, you name them, right? And last but not least, when we think about building services, you might need infrastructure and put some application building blocks on top of that. You might want to develop application and don't care about infrastructure and just develop code, as in the case of Julia Run. And for sure, you will also have to deal with data, right? So we offer those three services: infrastructure, application building blocks, and data analytics. Also, in terms of choice, and specifically around running computational intensive jobs, the plethora of computational units, VMs that you can request is extremely comprehensive. You can go from very commodity hardware to very high premium hardware, right? You all have been asking about GPUs. We have GPUs, servers, from 1 GPU up to 4 GPUs at the moment, NVIDIA GPUs, K80, M60, depending on the workload. For highly distributed services, we have also extremely high performance networks, right? Like for instance, we have InfiniBand networks that typically provide microsecond latency between nodes. Obviously, with InfiniBand, that comes with a premium price. We are also offering as a private preview what we call Azure Accelerator Networking, which in essence is networking based on FPGAs. So that means that you will get much more bandwidth in the range of 25 gigabytes per second, much faster latency, and also much better performance from your CPU, because you actually offload the network traffic to the FPGAs, and the CPU cores are absolutely free to run computational jobs, right? So that was a quick overview of all the benefits that if you run Julia on Azure you will get, and of course the benefits that Julia Computing gets by running Julia Run on Azure. The key point here is that Microsoft is super excited about partnering with Julia Computing, and we look forward to seeing all the great things that you can do. Thank you very much for your time.
So first off, who we are. So our background is from Morgan Stanley. There's a team of about 9 of us that have all come from there. And we basically are an independent kind of small startup company that is allowing clients to benchmark their and look at their currently FX transaction data, and in trying to determine whether they're achieving best execution. So looking at the performance of their trades with various different counterparties that they might be trading with, to compare all of the different people that they're trading with, all the different execution styles, and so on and so forth. I think the key point to highlight about us is that we are the only truly independent provider in this space. So that's what sets us apart from the competition in terms of TCA. As it says here, we've got a range of different clients, including hedge funds, asset managers, banks, and so on. So this is an area I don't know too much about, but there's a lot of regulation coming down with MiFID II, which is forcing on all these different firms the that they have to prove that they have done everything possible to get the best results for their clients. So part of this is where Bestix comes in, is to actually demonstrate via our analytical models and looking at the trades that our clients provide us, to try and show sort of potentially on behalf of banks that their solutions are performing well, and also for the actual clients that may want to compare the different providers, they can see where they're getting the best execution. So why Julia? Well, we started looking at Julia back at Morgan Stanley. So we used to use a lot of MATLAB, and we had a lot of problems with actually integrating that in our production environments. And it's something that Viral mentioned at the very start, the actual process of building the models, bringing them forward for actual production usage was a real pain, and we were rewriting things all over the place. And what we were looking for was something that we could write, sort of have our quants actually writing their models in, and not having to then translate those models into another language that we could productionize. So this was where we started looking at Julia, and we found that it's been fantastic really in achieving those goals. So it's basically means that Pete and our quant team can actually build all their models in Julia, and that's what we're actually running in production. We don't have to have any kind of stuff sitting in between the two. A couple of other things we did. I mean, I mentioned we looked at, we're using MATLAB in the past life. We also looked at Python and R, but we weren't able to get the performance that we have been able to get from Julia, and that's been one of the big benefits of using Julia for us, in that we're able to run our analytical models on thousands of trades, and it runs in seconds rather than sort of sitting waiting for half an hour. A couple of other things to mention. So we are running all of our platform on the Amazon cloud. So we're just spinning up Docker containers with these Julia processes as and when we need them, which is very easy to do. And we've been able to, so our platform, as I will demonstrate shortly, is web-based. So the actual integration between the web front end and the Julia back end and analytics engine is seamless. So I'll cover a few of these and then I'll go into a demo. So at the moment, what we've got, so our first application that went live about 3 months ago or so now, that we're running with a few clients, is our post-trade application. So what that allows you to do is to take a big portfolio of trades that you've executed already, you upload them to us, and we can analyze them for you. As part of that, we use Julia for all of our, as I mentioned, for all of our models, for all of the model calibration, in conjunction with a few Python libraries that I mentioned there. We also use it for all of our market data processing. So we have a couple of different market data feeds that we pull in and process, and that we're using then to benchmark the trades against. In the future, we're looking at our pre-trade application, which is sort of, rather than taking trades that have already been done, it's looking at trades that you are looking to do in the future and giving you a sense of what the best way to execute might be. And we're looking at potentially using machine learning as part of that solution. And so we're looking at a number of the libraries and stuff that's mentioned there, including Julia Run, which we're certainly interested in. So this is the kind of main screen of our app, and what I'll do, just as a test, I will hopefully, if I can find them. So basically just put together a sample spreadsheet. So this is just some sample trades that we've done that we want to analyse. So we've uploaded those, and then I'll submit that. So that portfolio of trades has then been passed off to Julia for analysis, and that's run within the time that you saw there. That's gone away. We've run all of our analytics, and that's what we're now showing. So the idea of the app is to cater to all different types of users. So as we mentioned, we've got lots of different types of clients, and they all want something slightly different in terms of the depth of analysis that they want to do, and the sort of metrics that they're interested in. So the way we look at that is to give you first a summary view, which is kind of a very high-level view of the various benchmarks and metrics that we've calculated. So we show, for example, on the top right here, you've got the top 5 trades performance in terms of spread, and the bottom 5. And then we break down the total traded volume in the various different ways, depending on the different information that you've given us in the trades. What we can then do is break that down. So, for example, we can say, I can look at a currency summary. So this will give you a range of different things. So this is specific to a sort of specific breakdown by currency. So it will compare all of the different trades that you've done. For example, if I look at this chart down the bottom here, it's comparing by the different currency pairs the actual impact cost of the trades in that currency pair. We then sort of break this down with this sort of nice visual summary on the top left, which is indicating, so the different sort of traffic lights are sort of are telling you whether the performance was good or bad, basically. So in terms of these different benchmarks, we then break that down along lots of different lines. So you can look at that by counterparty. So you can, if you've traded with several counterparties, you can see here we've got a few different banks. You can see that, for example, Bank G here was giving you a pretty good execution because you've got lots of green lights, whereas perhaps Bank B, not quite so good. And you can then drill down into all of these different metrics. So I can either turn these around and look at the actual underlying data in here. We then have our trade inspector, which is actually looking at individual trades. So, for example, I can select this algo. So we've got this Aussie dollar algo for about 43 million, and you can then see all of those metrics that we had summarized on the other screens actually for this particular trade. So you've got the performance versus all the different benchmarks, the reval, which is the comparison against the actual price, the mid price over the period, the sort of 10-minute period of the trade. And then we've got things like the fill info, which is giving you a breakdown of all versus the ask, bid, and so on and so forth. As well as for our algo trades, we give you even more information, things like the signaling risk. It's sort of an indication of when you've done an algo, actually how obvious it is in the market that that is an algo trade. We've then got your obvious kind of export. So one thing that a lot of our competitors do is they will give you some of these sorts of analytics, but they'll give you a very simple PDF. So they'll give you an end of day PDF or a monthly PDF with all your trades and the analytics. And we do provide all of that stuff, so you can download these things to PDF or CSV, while at the same time we then do also give you all of the the flexibility of the web UI. And I think that's about all I wanted to say.
Great. Thank you, Matt. Any questions?
Sorry, what's your graphics and user interface? What's that built in?
So it's Angular. It's all JavaScript and Angular.
You say you've got a mid price there. How do you get a mid price in FX? I mean, is that from the stuff that your client's providing you, or presumably if you went to a different ECN, you get a different mid?
Yeah, so we've got a few different data sources, and we're sort of aggregating our different data providers.
Your own one out there.
Yes.
And then where are you storing all your tick data? That's just curious technical thing. As you put out the cloud, are you using Influx DB or using?
So all of our actual tick data is on disk files for speed.
Plain text files.
Yeah, all zipped and.
Use this tick data?
Potentially, yes. It might certainly be something that we'll be looking at.
And do you use Julia for your real-time connectors?
For our real-time connectors, in terms of our market data. We do use it for processing the market data, yeah.
So Julia's role is about the analytics behind this job?
Yeah, so it's kind of dual role. So everything that you see on the screen, all of the analysis that's gone into that is all Julia. And also when we were saying when we get the market data, that's all processed by Julia as well.
What's the advantage of using Julia?
So for purely for the modeling perspective, it's both speed and the fact that we don't have to model it and then convert it into another language. So our quant guys are able to kind of write this, actually build all their models in Julia, and that's what we productionize. So there's no need to convert it into something else to make it more performant. That's probably our big benefit.
Thank you.